Hello everyone. In the beginning of the class, let us see new announcements. Okay, the first new announcement is May 4th, 2022. Class, class videos uploaded. Hello everyone. I have uploaded the class videos of May 4th, 2022 to YouTube. Their URLs are this, and this. Best regards, Wei Zhen. Okay. Next, the slides of Chapter 3 has been updated, version 2022-0509. Hello everyone, I have uploaded the latest version of the slides of Chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website. Multiple input, multiple output techniques for wireless communications. Course content, slides, chapter 3, slides 2022-0509.pptx. Best regards, Wei Zhen. Okay, the next new announcement is the handout of Chapter 3 has been updated, version 2022-0509. Hello everyone, I have uploaded the latest version of the handout of Chapter 3 to the eCourse2 website. The location and the file name are eCourse2 website. Multiple input, multiple output techniques for wireless communications. Course content, handouts, Chapter 3, handout 2022-0509.pdf. Best regards, Wei Zhen. Okay, next let us look at the progress of the last class. Okay, in the last class we have taught to Chapter 3 slides, pages 123.1 are finished. Okay, however, before we begin to continue the progress of the last class, okay, we need to introduce some problem and solution in the handout of Chapter 3. Okay, please open the handout of Chapter 3 and turn to page 53. Okay, and please turn to problem 15. Okay. Okay, problem 15, what is a magma? Okay, solution, it is beyond the scope of this course. Okay, problem 16, what is the empty function? Solution, it is beyond the scope of this course. Problem 17, what is a submonoid? Okay. Solution, it is beyond the scope of this course. Okay, problem 18, what is a multiplicative identity? Okay, why do we need to know what is a multiplicative identity? Okay, let us search for this problem now. Okay, because it appears in the solution to problem 4, what is GF of 2? Okay, and the GF of 2 appears in the solution to problem 3. What is F2n? And F2n appears in the solution. Okay, solution. Okay, here. Okay, to problem 2. What is maximum likelihood decoding? Okay, let us go back to the handouts. Okay, solution and identity with respect to multiplication is called a multiplicative identity, often denoted as 1. Okay, problem 19. What is a quotient ring? Solution: it is beyond the scope of this course. Problem 20. What is the ring of integers? Solution: it is beyond the scope of this course. Okay, problem 21. What is an ideal? Solution: it is beyond the scope of this course. Okay, problem 22. What is the Cartesian product? Okay, why do we need to know what is the Cartesian product? Okay, let us search for this. Search for Cartesian product in this document. Okay, because the Cartesian product appears in the solution. Okay, to problem 3. What is F2 to the power of n? Okay. Okay, solution in mathematics. Specifically, set theory, the Cartesian product of two sets A and B, denoted A times B, is the set of all ordered pairs AB, where small a is in capital A and small b is in capital B. In terms of set builder notation, that is, A times B is equal to the set of all ordered pairs AB, where small a is in capital A and small b is in capital B. Okay. A table can be created by taking the Cartesian product of a set of rows and a set of columns. If the Cartesian product rows times columns is taken, the cells of the table contain ordered pairs of the form row value, okay, column value. Please see figure 2. Okay, figure 2 shows the Cartesian product A times B of the sets A, which is equal to xyz, and B, which is equal to 1, 2, 3. Okay, in this figure we can see that the set A is equal to xyz, and the set B is equal to 1, 2, 3. And the Cartesian product of A and B, denoted by A times B, has 9 ordered pairs, okay, which are x1, x2. Okay, let me change the pointer. Okay, and I cannot change the pointer. Okay, and x3, and then y1, y2, and y3, and z1, z2, and z3. Okay. Okay, let us go back to the first figure 2. Okay, problem 23. What is a binary code? Okay, what is a binary code? Why do we need to know what is a binary code? Okay, because it appears in the solution to problem 2. What is maximum likelihood decoding? Okay, solution. A binary code represents text, computer processor instructions, or any other data using a two-symbol system. The two-symbol system used is often 0 and 1 from the binary number system. Okay. Excuse me. Okay, let us go back to excuse me. Go back to chapter 3. Please open the slides of chapter 3 and turn to page 123. Okay, we are looking at, let me change the pointer. We are looking at the results for NR. NR is the number of received antennas, which is greater than or equal to NT. NT is the number of transmit antennas. For example, examination verifies that the sum of the eigenmode gains is equal to 1. Okay, let us go back to table 3.3. Okay, you can see that when SNR is equal to negative 10, P1 plus P2 plus P3 is equal to 1 plus 0 plus 0 is equal to 1. Okay, you can check for other SNR values, and you will find that the summation of P1, P2, and P3 is always equal to 1. Okay, secondly, we note that at low values of rho, only eigenmode 1 is assigned a non-zero gain, consistent with table 3.2. Okay, let us go back to table 3.3. Okay, we can see that for SNR is equal to negative 10 to negative 7 dB. Okay, only P1 is assigned by a non-zero value. Okay, that is which is equal to 1. And P2 is equal to 0, and P3 is equal to 0. Okay, consistent with table 3.2. Okay, let us go to table 3.2. Okay, when signal to noise ratio is a rho approaches 0, the water filling performance places all power in eigenmode with largest eigenvalue. Okay, that is P1. Okay, let us go to page 123. Okay. Thirdly, we observe that as rho increases, the eigenmode gains become increasingly close in value, again consistent with table 3.2. Okay, let us go back to table 3.3. Okay, you can see that as SNR increases, okay, P1 from 1 becomes smaller, and P2 from 0 become larger, and P3 from 0 become larger. And finally, when SNR is equal to 30 dB, P1 is equal to 0.3338, which is approximately 1/3. And P2 is equal to 0.3336, which is approximately 1/3. and P3 is equal to 0.3326, which is also approximately 1/3. Okay, again consistent with table 3.2. Okay, let us see. Okay, in table 3.2, when signal to noise ratio ρ approaches infinity, the water filling performance applies equal power to all eigenmodes. Okay, let us go back to page 123. Okay, next page. Next, let us go to section 3.7.2. Resource for NT being greater than NR. Okay, the capacity resource when NT is greater than NR are qualitatively different in certain respects than they are when NR is greater than NT. Okay, figure 3.5. Let us go to figure 3.5. Okay, we can see that in figure 3.5, it shows the comparison of theoretical capacity predictions for H2. Okay, we will explain what is H2 later. Okay, for the x-axis, the signal-to-noise ratio is from negative 20 dB to 20 dB. And in the y-axis, it is the bits per channel use from 0 to 20. And there are 4 curves in this figure. The first one is equal power allocation, denoted by the solid curve. Solid line, okay, this curve. And the second one is the single mode eigenbeamforming, okay, denoted by the dotted line, dashed line, okay, this curve. Okay, the second one is the eigenbeamforming, denoted by the dash and dotted line, okay, this curve. Okay, finally, the SISO, okay, single input, single output system. For the SISO case, it is denoted by the curve, dotted line, okay, this curve. Okay, previous page. Figure 3.5 compares the theoretical capacity predictions for a 4x3 MIMO system using a 3x4 channel matrix H2, which we derive from H1. Okay, what is H1? Let us review it. Okay, in page 115. Okay, H1 is equal to this channel matrix, which is a 4x3 channel matrix. Okay, let us go to page 125. Okay, from H1 as follows. H2 is equal to H1 transpose. The equation number is not in the correct position. Okay, let me correct this problem. Okay, sorry, it should be 3.40. Okay, so 3.4. Okay, please wait for me. 3.40. Okay, 3.40. Okay. Okay, good. Okay, so next page, we have seen this before. This is figure 3.5. Okay, for a full rank channel such as H2, okay, NT is greater than NR, which is equal to R. Okay, because R is the channel rank, okay, which is equal to the minima of NT and NR. Now because NT is greater than NR, so NR is equal to R. And how do we know H2 is a full rank channel? Okay, because H2 is equal to H1 transpose. Okay, and H1 is equal to this matrix. So after taking the transpose on this matrix, and use the technique you have learned in the course linear algebra, you can find this matrix is full rank. That is, the rank of this matrix is equal to 3. Okay, let us go back to page 126. Oh, sorry, next page. So there are more transmit antennas than eigenmodes that can carry independent data strings. Okay, there are 4 transmit antennas, and the number of eigenmodes is equal to R, which is equal to 3. So this channel, this MIMO system can carry 3 independent data strings. Okay, the implication of this is that the equal power allocation strategy is wasteful because it attempts to excite more eigenmodes. That is, the equal power allocation strategy attempts to excite 4 eigenmodes than the channel can support. Okay, the channel can only support R eigenmodes. Okay, that is 3 eigenmodes. Instead, it should place more energy in fewer data streams. Okay, that is, place energy in 3 data streams. At large SNR, we have seen that the water filling algorithm used with eigenbeamforming allocates the same power to all R eigenmodes. Okay, let us go back to table 3.2. Okay, so we can see that we can see that when the signal to noise ratio rho approaches infinity, the water filling algorithm applies equal power to all eigenmodes. Okay. Okay. For this reason, we would expect equal power allocation capacity to be less than the capacity associated with eigenbeamforming in general, and that at large SNR, the degradation in performance should be equal to this equation. Okay, we can see that degradation is equal to 10 times log 10 of NT over R. Okay, because actually we only can support R data streams. Okay, but now we use NT data. We expect to excite NT data stream. Okay, so this is the degradation. Okay, again the equation number is in the wrong place. Let me fix this problem. Okay, good. Okay, let me change the pointer. Okay, it is 25 minutes. Let us take a break.